Okay, let's start. The second speaker is Kwon from Seoul National University. His title is Crystal Basis for General Linear Lie Superalgebra 2. Please.
Yeah, thank you. Thanks for the introduction. So let me start the second part of my lecture. So yesterday, I briefly introduced what the quantum superalgebra associated to GLMN. And then we talked about the crystal base of certain family of finite dimensional irreducible representation, not all of them, but very special one, which arise from the Chauvet duality, so-called polynomial representation. And then so the existence of the crystal base for the polynomial representation and the crystal structure or its combinatorial realization. So today I want to introduce another family of finite dimensional representation of GLMN or its UQGLMN, which also plays important role when you study the finite dimensional representation of GLMN. And then I will introduce the crystal base for this Q-deformed Castle module. Okay. Yeah, so anyway, we have seen at least one example of the of modules which have crystal base. And next natural question might be whether we also have a crystal base of a Bowman module for U sub Mn, as in the case of a symmetrizable Casimir algebra. But the one problem, which I of course mentioned yesterday, is that as far as I know, we do not have a natural inverse system of the crystal of the polynomial representation, so that we can take a limit to have a crystal structure of the negative half of the quantum group UMN. So let me briefly remind you what can be actually done in case of GLM. So let's consider only the GLM0, so just the crystal for the GLM. Then for two dominant integral weights, say lambda and mu, we can think of a partial order where the difference, so mu is greater than lambda when the difference mu minus lambda is a dominant integral weight. Then there is a natural embedding of a crystal from Bm of lambda to Bm of mu, which is given in this way. So X is, so any crystal element of B of lambda can be given like this form, where X is the product of crystal operators, finite number of crystal operators, Fi. Then we just apply the same operator to the highest weight element in B of mu. Then this gives a well-defined crystal embedding. And then if we take a limit, then this gives the B of infinity. Okay. So we want to do the same thing, but the problem is that there is no natural partial order on the set of Mn hook partitions which parameterize the highest weight of our polynomial representation. Okay. So instead of go directly to the crystal of Bowman module, we will think of another representation called the so-called the Castle module. So it is roughly speaking, it is a finite dimensional indecomposable highest weight module, or roughly corresponds to, can be viewed as a parabolic Bowman module when in the study of BGG category. Okay, so here is the thinking diagram of the quantum superalgebra or U sub Mn. Then we want to think of a certain parabolic Balmer module. And actually, we take the maximal Levi algebra of even type. So that means we ignore the only odd isotropic simple root. Then if we erase that simple root from our thinking diagram, then we have a disjoint union of two finite type of the thinking diagram of finite type A. Okay. So we consider the subalgebra, say U m, n, which is generated by the same Cartan part, and the Chevalier generators are corresponding to our maximal Levi subalgebra with two disjoint type A. So we want to start from the irreducible finite dimensional representation of this Levi subalgebra. So to parameterize its finite dimensional irreducibles, we need the following set. Say P to the plus. So it's a linear combination. So it's a weight in P where it is a dominant integral weight with respect to our Levi subalgebra. So the first m coefficients are weakly decreasing, and also the other coefficients, remaining coefficients, are also weakly decreasing. And let me denote by the lambda plus the first dominant integral weight, and lambda minus the next dominant integral weight. Okay, then we define the v m, n of lambda to be the irreducible highest weight module with highest weight lambda with respect to our Levi subalgebra. And then we can easily extend the action of Levi subalgebra to the parabolic subalgebra, where which is generated by U sub mn and E sub m. And here we define the action of E sub m to be trivial. Okay, then it is a P module, and then we take an induction to the quantum group U sub m/n. So let me denote it by K of lambda. Then here it is easy to check that it is indecomposable highest weight module with the highest weight lambda. And then by standard arguments, we can take its maximal quotient. So say if we mn of lambda. So be careful when here lambda denotes the arbitrary, the dominant weight P plus here. So sometimes we use the notation for the mn hook partition when we consider the polynomial representation. So anyway, here this is a maximal quotient of K of lambda. So yeah, in this lecture, the main goal is to explain the following theorem. So first we can prove that this K of lambda has a crystal base where the associated crystal, say B of K lambda, also has a connected graph structure. And moreover, when the highest weight is corresponding to, when it corresponds to the mn hook partition, so that the corresponding irreducible representation is a polynomial representation we talked about yesterday, then we also have a canonical projection from the K of lambda to this polynomial representation. Then this projection is compatible with the crystal base of each module. So that means the crystal lattice L of K of lambda goes to the crystal lattice of the polynomial representation. And also it induces the map from the crystal of K of lambda to the crystal of the polynomial representation. So it goes to the crystal of this V of lambda or 0. And of course, I haven't defined yet what the crystal base means here. So, and of course, for Okay, so here we should define the crystal operators for the isotropic simple root, the alpha n. Okay, I will explain in the next slide or later. Yeah, so we to construct a crystal base of this K of lambda, we use a PBW type basis for the negative part of this quantum group. Okay, and yesterday we have seen that the set of positive roots or the root system is for GLMN. The super case is exactly the same as the GLM plus n, but there is a parity of the roots. Okay, so anyway, let us recall that the set of positive roots which are even is given by this delta A minus delta B, where the indices A and B are of the same parity. And the set of odd roots are the roots of this form where the two indexes are of different parity. Okay. So we want to, so we consider the root vector and then consider the PBW type monomials. Then using that PBW monomials, we want to construct a crystal lattice. But here we choose a special order on special convex order on the set of positive roots. So more precisely, we consider oriented thinking diagram of A m plus n minus 1, and then our orientation is has a single sink where the only sink is the odd isotropic simple root. Yeah.
I checked out my understanding. Long time ago, John Brown was talking about so those simple constituents of the cosmology or not.
Simple.
Well, composition factor.
Yes, right. Yeah, that's right. Yeah. Yes, I will show in a couple of minutes later that that actually this CAS module is a finite dimensional. So it's a finite dimensional indecomposable, and actually the composition multiplicity of the simple factors in CAS module was a fundamental problem. Yeah. Okay, so we choose a special reduced expression of the longest element of this symmetric group. Then we have a corresponding convex order on the set of positive roots of this type A. Then if we visualize the convex order corresponding to that reduced expression, then it looks like this. Okay. Of course, you may notice that it's one of the outline on the right and quiver, the concave over type A. So here here in the middle, the rectangular part in our diagram, this consists of the odd roots. You can see that. So I draw it in pink, and the other roots which are given in blue are the even roots. So that's the arrangement I would like to work with. And also here, the plus and minus denotes the blue ones. They are the even roots. And the plus denotes the positive even roots with the positive norm square, and the other is the negative norm square. Okay, yeah. So we want to think about the PBW type monomials with respect to this convex ordering. And the red ones or pink ones are the odd root vectors. So using that PBW type monomial, so I want to think about not yet the U minus, but with the K of lambda. Okay. So our root vectors are defined in the following way. So okay, here when the root is a positive even root, so which are located in the blue triangular part, then we define, as in the usual case, we use the Lustig transformation to define the root vector. And for the odd ones, we also define in a similar way as in the case of type A, using the Q commutator to get the vector, root vector corresponding to the odd ones, so, which are located in the rectangular part in pink. Okay, so if beta is given by, so if beta is an odd root vector, then it's some of the simple roots where the alpha m isn't necessarily included. So we define the root vector f beta using the Q adjoint, where this is defined in the following way. So it's the same as in the usual case, but here, as I mentioned yesterday, we replace all the Q to the something by the bold Q function. Okay, so that's our root vectors, and the convex orderings are in the previous slide. And then all the effects actually which holds in the case of type A, exactly the same fact is true here in this case. So only difference is that the Q to the something is replaced by our bold Q functions. So for example, there is a Lewandowski-Soberman relation, which are of the same form. So here, if when beta and alpha are the pair of positive roots, beta is the bigger one. But if we consider the Q commutator of the F beta and F alpha, then they satisfy the following form. It's a very well-known formula. And the additional relation in this case is that here the roots in this rectangular part is an odd root vector. So we can check that the square of this root vector is 0. So as in the case of usual enveloping algebra of the Lie superalgebra, here the root vector square of the odd root vector is 0. So that kind of relation is actually needed when you prove the existence of the crystal base of the K of lambda. Okay. So we consider okay, here anyway, so we have a PBW type basis of this U minus, where this product of the root vectors we have defined just before, and the ordering is given in the convex order. And the only difference compared to the usual case is that the multiplicity of the roots is 0 or 1 when the beta is odd root vector. And that gives a K-linear basis of the negative part of the quantum group. Okay, that's a very general fact. And now we focus on certain subalgebra of U minus. So we consider the K subspace of U minus, which is spanned by the product of root vectors, only we take the odd root vectors. Then this subspace, say K, is actually the subalgebra generated by the odd root vectors. Then using this fact, we can say that we can decompose our negative part of the quantum group in the following way. So we can separate this subalgebra, this algebra, into the K and the negative part of the Levy, the quantum group of the Levy subalgebra. So UMM minus. Okay. So this decomposition is, we need this decomposition to think of this isomorphism. So K of lambda is the induced representation. Induction is taken from the irreducible representation of the Levy subalgebra. And then if we want to, so we want to think about it's a linear basis, then using the decomposition in the above, then we can say that the K of lambda is isomorphic to the K times and Vm comma n of lambda. So it's also it is a tensor product of K and M0 lambda plus, and then V0 and lambda minus. Okay. And then immediately we can see that the dimension of k lambda is finite dimensional because here k is linear basis is given by this kind of monomials, and the degree of each outer root vector is just a 0 and 1, so it's finite dimensional. So our k of lambda is a finite. So the tensor product here are all the finite dimensional. So our k of lambda, this in this representation is finite dimensional. And also its character, it looks like you can easily compute that the character k of lambda is the product of the character of k, the subalgebra k, and the irreducible representation of Levi subalgebra. And more explicitly, it is given by the product of the two Schur polynomials, one from M0 and the other from 0n. And that product part is the character of our subalgebra k. Okay. So it can be viewed as a so-called the Kess module. So let me call it the Q-deformed Kess module. Yeah. Yeah, and the reason why Kess module was people studied more seriously, the Kess module is that if we focus on the representation theory of finite dimensional representation with general linearly superalgebra, then in that category, Bohm module doesn't belong to that category. So we need another standard object in the category of finite dimensional representation with GLMN. So the Kess module plays that role in that category. So as just so in the previous question was that one of the most important problem was it's almost 20 years ago to compute the computational multiplicity of Kess module, simple module in the Kess module, and it was solved by Brunden using some canonical based theory. Okay, but that topic is a little far from this lecture, so I will let me go on to the crystal based theory again. Okay, so I want to construct the crystal base of this Q-deformed Kess module. And okay, so first I would like to define more precisely again what the crystal operators should be here. So as in the case of polynomial representation for the SL2 copies, so the crystal operators are lower or upper. So if the simple roots has a positive square norm, then we define the crystal operator for that simple root to be the lower crystal operator. And if it is negative, then we use the upper crystal operator. And the reason for that was explained yesterday, which actually due to the definition of the defined relation of the quantum superalgebra, where so there is some how to say. So the defined relation was rather twisted depending on the sign of the square norm of the simple root. So yeah, if we look at that defined relation, then we should consider lower and upper separately, depending on the sign of the simple root. Okay, and here we also the operator to be for the other isotropic simple root, we define the operator to be just the left multiplication. But here the inverse operator EM tilde, we use the Q derivation. It's not equal to the case of polynomial representation. Okay. Okay. So let me give a brief sketch of the proof. So let me first talk about the existence of a crystal base. Okay. So let's first consider some general facts related to our subalgebra K, which is generated by the other root vectors. Then maybe you remember that yesterday when we give a very general introduction to the Lie superalgebra GLMN, if we look at the enveloping algebra of its negative part, then it was U of GLMN, say plus or negative, is isomorphic to the enveloping algebra positive part of its Levi subalgebra. It's a positive part, and then the enveloping algebra of the subalgebra generated by the other root vectors, right? Then we have seen that we can check easily that it is actually isomorphic to the exterior algebra generated by the CM tensor C, and one of them was I think here is CN star is a dual. Anyway, it was just the exterior algebra. So here in this case, the K, so now we are considering the Q deformation. So we can check that this algebra K is actually the Q deformed exterior algebra generated by Q deformed exterior algebra generated by this n times n dimensional space. Yes. So what is the Q deformed exterior algebra here is that basically I follow the construction in one of the references, the Denis Ugolov. Actually, there is a Q deformed Fock space construction, but before that there is a general construction of finite dimension Q deformed exterior algebra. So I follow that convention. So in that sense, our K is isomorphic to the Q deformed exterior algebra. And our root vector, other root vector F beta, corresponds to this standard basis. Okay, and from on the right-hand side, or as a Q deformed exterior algebra generated by that space, there is a natural action of the quantum group of actually gel m plus gel n, or more precisely, there is an action of UQ gel m tensor UP gel n. Here P is a minus Q inverse on our Q deformed exterior algebra. And of course, this is isomorphic to our Levi subalgebra of UM/n. So by and also we can check that this isomorphism. So the joint action of this Levi subalgebra on the Q deformed exterior algebra, when you pull back via this isomorphism, then it coincides with the usual Levi subalgebra action on our induced representation. So as a module of this Levi subalgebra, our K0 is isomorphic to the how to say? Yeah, the induced action is isomorphic to the K0, the induced representation. Okay, so that's one key observation to construct the crystal base of the KES module. Okay, so our K of lambda is isomorphic to. So then we can also check that our K of lambda is actually isomorphic to. So as a module over this Levi subalgebra, it is isomorphic to the tensor product of this Q deformed exterior algebra and the polynomial representation. Okay, and now define our crystal lattice and its associated basis at K equals 0 to be just the A0 span of our this monomial, and then its image at Q equals 0. Okay. And more generally, we define L of K of lambda to be the tensor product of this A0 lattice, and then by the lattice of our polynomial representation. It's very natural. And B of K lambda is the induced the basis at K. BK plus minus, oh yeah. So why I'm using the plus minus sign here is that unlike the case of symmetrized over Casimir algebra, in the definition of a crystal base, in the case of a super, we define B to be the kind of pseudo basis, so that it's a union of B and minus B, where B is a linear basis at Q equals 0. So that's why we put plus minus here.
I'm still confusing.
Yeah.
In my brain, if Q to 1, so it is necessary only using the plus. Why?
So, okay, in super case, when it, okay, so B of K is not, this itself is not a linear basis. Actually, we have to mod out by the plus minus to have a linear basis. Yeah. But sometimes in super case, when you apply the crystal operators, then sometimes plus minus appears. So we have to ignore it. So that's why we consider signed basis. Yeah. So yeah. Yeah, then if we define the Lk of lambda B of K lambda, then it forms a crystal base of K lambda as a Levi-Server algebra. And one important factor is that the L of K so we have to check that it is a lower crystal base with respect to UN0, and we have to check that it is also upper crystal base for the U0N. And then this fact actually can be checked directly. And also this was already implicit in the structure of the bimodule structure on this Q deformed exterior algebra. So it forms a crystal base with respect to, and also here the crystal means that the operator is a lower and upper corresponding to the sign of the even simple root. So it forms a crystal base with respect to this one. So finally, we have to check that it is also invariant under the odd crystal operators, and still we can prove. And in this case, if we consider the monomials consisting only the odd root vectors, then the operator looks very similar to the case of a usual crystal, PBW crystal on the type A, so that the applying X should be at E, sorry. Yeah, so which one? So +1. So applying FM tilde to our monomial changes multiplicity at the simple root alpha m by alpha m plus 1 when it is 0. Yeah, 0. Otherwise, oh yeah. yeah, in this way, yeah. Yeah, and okay, and also this kind of monomial, which is the linear basis of our subalgebra, can be identified with this just collection of its multiplicity, which is 0 or 1. So it can be also identified with certain a subset of the set of positive odd roots. So we count the odd root vector if the multiplicity 1, and do not count if it is 0. So that corresponds to a bijection between the power set and the crystal B of K. Yeah. Okay, so our crystal B of K lambda is a very concrete form. So it is a product of three sets. One is the power set of odd roots, set of odd roots, and the crystal of the M0 lambda plus and crystal of V0n of lambda minus. And of course, we know that these are already very well-known crystal of type A, or can be realized as a Young tableau or semi-standard tableau. Okay, so that's our crystal model. Yeah, actually, B of K lambda, its a crystal structure, can be described explicitly as well. Because the UMN crystal, Levy subalgebra crystal structure is already well known, just the usual type A crystal. And also we just apply the tensor product rule because as a module over the Levy subalgebra is here, where is it? Okay, here. So K of lambda as a module of its Levy, it is isomorphic to just the two tensor product of two finite measure representations. So we just apply the tensor product rule. Okay. And also we can, even though we construct the crystal lattice in a very concrete way, but anyway, we can also prove that this crystal lattice also can be given in a more general form, which looks more like the crystal lattice given in the case of symmetrized Casimir algebra. So L of K lambda is equal to the A0 span of that kind of monomials where is given by applying the crystal operators E or F to the highest weight vector. Okay, and also we can check the connectedness so that we can prove the uniqueness of a crystal base up to scalar multiplication on the highest weight vector. Okay, so next I want to talk about this compatibility of the crystal base of Cas module with the crystal base of polynomial representation. So
May I ask again?
yeah, sure.
At the level of the crystal, can you see the decomposition the crystal into kind of simple guys?
No, because we do not know the crystal base of it. Simple ones.
Oh.
Yeah, we only know the polynomial representation. Yeah, yeah. It's also this kind of the answer is also for the symmetrizable Casimir algebra. So we know the Volma module, but we only know the crystal of the integrable highest weight module. So it doesn't help to calculate the compression multiplicity. But anyway, let me recall some general fact on the Cas module or Q-deformed Cas module. So there is a good equivalent condition for a Cas module to be irreducible, like the irreducibility of Volma module. So it is known by, so in case Q equals 1, it was given by Cas that this Cas module is irreducible when the highest weight lambda is typical. So the typical is some technical condition, but anyway, the typical means that if lambda, when it is shifted by the row vector, which is the half sum of the positive even roots minus the half sum of the positive odd roots, then if we pair with any odd root vector, if it is 0, then we call this lambda is typical. Then it's equivalent to saying that the K of lambda is irreducible. Okay, so rather technical, so you don't have to remember that condition. But anyway, in our case of polynomial representation, this typicality looks more combinatorial. So in case of Hook partition, if the corresponding highest weighted capital lambda sub lambda is typical, is equivalent to saying that our partition lambda contains this rectangular partition. So m sub n, m to the n means that it's m this should be n to the n, sorry. So MN hook partition means that we consider a large hook. The size of it is n, it is m. So the rectangle here is the n to the n. And the lambda is typical if and only if it contains this rectangle. So if lambda is contains this kind of rectangle, then our k of lambda is equal to the polynomial representation itself. Okay, so here is some technical argument for the proof of the compatibility. But anyway, let me briefly explain. So here is our projection, which you are interested in, say pi lambda. Then, so we want to prove that the crystal base is preserved under this, compatible with this the projection net. So to prove this, we consider the following diagram. So here, from lambda, we shift our highest weight by some positive multiple of the delta plus. Delta plus is the sum of the delta 1 and delta m, which is just the weight of the determinant representation of GLM0. And if large enough, then we can say that the lambda plus L delta plus is typical. So we replace lambda by this typical weight and its Cass module. Then with respect to this highest weight, we consider the projection to the polynomial representation of the same highest weight. Then in this case, we know that this is typical, so it is isomorphism. And now we consider this polynomial representation. And okay, so this polynomial representation is embedded into the tensor product of highest weight lambda and L delta plus. Since it is a semi-simple, so there is actually one factor with the highest weight lambda plus L delta plus. Okay, so there is a natural embedding. And also we can take not UMN linear, but UMN minus linear, which sends this kind of vector with tensor, which is the highest weight of vector of this second vector, which maps this vector to the V. Okay, so we consider this diagram then, and theta, the vertical maps is here is just U minus linear isomorphism, and here theta L is the composition of these two maps. Then from this diagram, we can check that except this projection, the other maps are preserving the crystal basis for each representation. Then we can say that since the diagram is commutative, our projection preserves the crystal base of the K of lambda to the crystal base, sends the crystal base of K lambda to the polynomial representation. So that's the proof of the compatibility. Okay. Okay, so the crystal of the Cass module maps to the crystal of a polynomial representation or 0. So some of them are going to 0. So that means that there is a embedding of the crystal polynomial representation into the crystal of the Cass module. And we have seen that the crystal of a Cass module can be, so by definition or by construction, it is the product of these three crystals. And also we can describe very, very concretely, in a combinatorial way, we can describe this embedding. Okay, so let me, in the remaining of my talk, I will explain how to construct this embedding. So here is a brief sketch of the map. Okay, so I will give a very concrete example in the next slide. So roughly speaking, so we start from here, where Bmn over lambda is just a set of semi-standard tableau. It's Mn hook semi-standard tableau. So we want to define a map which sends this T to the triple of this of data. So one is the subset of the positive orders, and the other two terms are the usual semi-standard Young tableau, which is of type AM-1 and AM-1. Yeah, so it's the algorithm is like this. So this part we just ascended to is the same. So we have to, so this part, that means T to the less than equal to M means that it's the subtableau of our T, which is obtained by just consisting of the first M rows. And the T greater than M plus greater than M. Yeah. So the other complement. Okay. So we actually T sub less than T less than equal to M is still MN Hooke semi-standard tableau. So there is a alphabet from 1 to M. Also, there is alphabet from M plus 1 to M plus N. So it's a mixed one. But we want to actually extract the information of the odd root vectors actually inserted in this tableau. So we have to extract the data corresponding to S. And for that process, we apply some maybe people working in algebraic combinatorics may know well, the so-called the Sagan and Stanley's skew RSK algorithm. I will show in an example in the maybe next slide. Okay. And also let me give a remark on the crystal structure of this CAS module, which is actually needed in the tomorrow's talk. Okay, so our B of K lambda is the product of these three sets. And so now consider the crystal operators. So if the crystal operator comes from the UM0, then the only first two factors are involved. And as a UM0 crystal, our B of K lambda is just the tensor product of the first two factors. And the tensor product order is from left to right. Okay. And if we consider B of K of lambda as a crystal over U0n, then it's the upper crystal operator, and the tensor product order is reversed, which I mentioned yesterday. So we regard it as a tensor product of 0 and as a tensor product of two the crystal P of pi 1 and B of lambda minus, but the tensor product order is reversed. And finally, the operator for the other isotropic root, this only the first factor is involved, where the multiplicity of the Fm is changed. Okay, so if we want to draw the crystal graph of this CAS module, the only part we need more information is this part, the crystal of the subalgebra K. Right? Okay, so let me give an example first for the crystal of the B of K0. Okay, so it's very simple. How many minutes? Okay, it's 10 minutes. Okay, so here is the arrangement of our odd root vectors. And okay, so the monomials consisting only of these odd root vectors may be identified with the multiplicity for each odd root vector, so that it can be also identified with a binary matrix over 3 by 4 or 4 by 3. Okay, so let us consider the crystal operator, how to compute it. Okay. So suppose that okay, let us first consider F1 tilde. So its norm square is positive. So suppose that the crystal element is given. Then F1 tilde actually is the delta A's which are involved with these crystal operators are only delta 1 and delta 2. So the corresponding odority vectors are here. Okay. And then so here each multiplicity is 0 or 1. Then we assign a plus minus sign according to its value, plus and minus. And then we make a sequence along the orders which I presented here. So 1, 2, 3, 4, 5, 6 in this way. Okay. Then we have a sequence of plus and minus, and then we just apply the signature. So that's the description of F1 tilde. And for the negative known case, it's almost the same game. So for example, if we want to consider F5 tilde, then F delta 5 and delta 6 are involved. So we consider the part of the multiplicity here, and then we give the order from here, 1, 2, 3, 4, 5, 6, and assign a plus minus sequence by the same rule, then we apply the signature rule. Yeah. So it's very, very explicit. Okay, so now in principle we can compute the crystal of the CAS module according to this structure. Right. And okay, so finally, let me describe an embedding of our crystal polynomial representation to the crystal of CAS module. Okay, so suppose that M is 3 and N is 4. And so that's the tableau yesterday. Okay. The shape is 5, 3, 2, 2. So it is a 3, 4 hook partition. Okay, and here, yeah, so its weight is the first 5 1s and 3 2s and 2 3s. And then we consider there is a 1 and 1. So 1 4 and 1 5. So now we want to assign a triple. The one is the subset of a set of positive odd roots and the two tableau. Here this is the same as the this subtableau. Okay, so this okay, it's okay. Yeah. Okay, let me describe it step by step. So t less than equal to 3 is the subtableau consisting of the first 3 rows, and the other part is the complement of it. So we don't care about that tableau, so we only consider the first one. So we want to extract. So the shape of this t less than or equal to 3, less than or equal to 3 is just our lambda plus, and we want to take purely Young tableau of that shape, purely consisting of the even alphabet. So we have to extract the information of the odd simple roots. Okay. Okay, so we first consider the subtableau here consisting of even entries. Okay. Then we need some manipulation by taking tensor product of the crystal of the dual of the determinant representation. So it's simple. So so 1, 2, 3 is the crystal of the natural representation, and here check is the dual representation. So it is the weight delta minus delta 3 minus delta 2 minus delta 1. So that's the dual crystal, and the determinant crystal of the determinant representation is just the tableau of single column, which is trivial. And its a dual one is the single tableau of the same height, where the entries are consisting of this one. So by taking the tensor product with this kind of trivial crystal means that we just invert the entries column by column. So the first column, if we take the tensor product with this one, then the weight becomes 0. So it's gone. And then if we take this tableau with this crystal, then it becomes the 3, 2 check, and then 3, 1 check, the complement. So in this way, so we apply 5 times. Actually, the 5 doesn't matter. If we take just enough tensor product with this dual crystal, then the map is well defined. Okay, anyway, we consider this kind of complement. Yeah, and the reason why we consider this subtableau is that, okay, so here the second factor in pink subtableau is the this one, right? So now we consider, so instead of separating the tableau with this blue and red, pink, we consider the pair of the same pink and now the complemented one. And in this case, we see that they are both skew shaped, but they share the same inner shapes. Okay. But the outer shapes are different. Okay, so if we overlap these two tableaux, then they have the same inner shape and share the common outer shape. Now we want to extract some entries of this tableau. Extract the entries which are overlapped. So, okay, what it means. So now we apply the inverse RSK correspondence. So this part plays the insertion tableau, and this part plays the recording tableau. Okay, so this is a semi-standard, so we just a standardization. So that, and then after that, according to the ordering here, we apply the reverse insertion. So first we start here, the 5 with index 1. Then we apply the reverse bumping. Then the resulting pair of tableau is here, and the extracted informations are 2 check and 5. So that gives the other simple root vector, del minus del 2 minus del 5. Okay. Then we continue this process until this recording tableau is empty. Okay, so we obtain a sequence of odd root, and then the resulting tableau on the left-hand side is like this, and then we apply the tensor product with not dual. It's not this. Okay, sorry. Now we apply the tensor product. Applying the tensor product with the crystal of the determinant representation 5 times again, then to have a tableau here whose shape is lambda plus. So there is no information of the odd root vectors. Okay, so the resulting information is that now we have a tableau shape lambda plus with only even entries, and here it's the same one. And now we have a subset of positive odd roots. So that corresponds to that is the corresponding element in the crystal of a Cass module. Okay, so finally, I'd like to mention that, yeah, this kind of insertion is already well known, but the important fact is that it is compatible with the crystal structure of the quantum superalgebra. So in special case, for example, suppose that our lambda is just a rectangle, so that the corresponding highest weight is typical, so that the polynomial representation is equal to the Cass module. Then our crystal embedding is just the isomorphism. So on the left-hand side, we have the MN Hooke semi-standard tableau. But if we separate this tableau with even entries and odd entries, and the even part, we take the complement by taking the tensor product with the dual determinant representation. Then we have actually a pair of 2 semi-standard tableau of the same shape. Then our process is just nothing but the RSK correspondence. But the important fact is that this correspondence is, of course, it is well known that this dual RSK correspondence is compatible with the crystal structure over GLM and GLN. But one extra fact here is that it also compatible with the crystal operator with respect to other isotropic simple roots. So it becomes an isomorphism over GLM and crystal. Yeah, that's what I talk about.
Are there any questions or comments?
So can you consider the CATS modules or its crystal for non-standard border?
Sorry?
So can you consider the CATS module or its crystal for non-standard border?
Non-standard border, yeah, it's a good question, but I haven't considered it. Yeah, yes, but it would be good. But I'm not quite sure where if we consider the non-standard border, then I'm not sure whether we have this kind of nice crystal structure.
So at least we can define the CATS module, right?
Yeah, CATS module. Yeah. Even for the CATS module, we can think of a non-standard case. I think we have to be more careful, yeah, because in the construction of a crystal base of K of lambda, we need the decomposition of the negative part. So yeah, so I haven't.
Okay, thank you.
You can do it. Yeah.
Any questions?
So if you take M and N both to infinity, I mean, since you get the Q wedge algebra kind of in the middle, can you say any sort of relationship with the Fock space and these kinds of constructions and the corresponding crystals?
Yeah, okay. So we can take the limit M and N to the infinity. Then we can naturally think of the analog of the polynomial representation. Now it's replaced by infinite dimensional, but still a very similar properties with the polynomial representation as well. And then I think we can naturally think of the CATS module as well. So you can naturally extend it to the infinite rank case as well. And the Fock space, Well, I'm not quite sure what kind of Fock space you are thinking of, but how to say, yeah. Yeah, so in the construction of polynomial representation, we start with natural representation, which corresponds to the Young diagram of a single box. But in the infinite rank case, we can start from, how to say, I think that in case when you think of a kind of a Fock space, then we can start from the fundamental type representation, where actually correspond to the single row column, and then we consider certain semi-infinite analog. Then we consider the tensor product, and then we have a kind of similar analog for the level rank duality kind of phenomenon. Yeah. So now in that case, there is duality between the UQGL infinite, GL infinite/infinite, and then we consider the action of a UQGL L. L is the level of the Fock space. Yes, we can think of a kind of analog. Yeah.
Thank you.
Yeah.
Any other questions? Okay, may I ask one
Yes.
question? So you have many good combinatorial structures. So it means you have a kind of combinatorial R matrix.
Yes, we can think of it. We can think of it in the finite type case, and also in the affine case. In the yesterday's talk, I mentioned one of my recent work with Professor Okado on the construction of a KL module and its a crystal for the affine type A super. And then in that case, we have also have a very nice combinatorial algorithm for the combinatorial R matrix on the tensor product of KL crystal.
Okay, thank you.
Yeah.
Okay, so if not, so red thanks the speaker again.